Welcome to the lecture titled Upline Identification of Process Dynamics. Earlier in our earlier lectures, we have seen relay control systems inducing limit cycle outputs, and when the relay is substituted by an equivalent gain, then the analysis of closed loop relay control systems become easy. In today's lecture, we shall see how upline identification can be done using equivalent gain of relays. An upline identification structure can be given like this, where R 0 equal to 0 when the relay is in action, whereas R 0 is not equal to 0 when the controller is in action. That means, when the controller is in action, the process is in operation, then the relay test cannot be initiated. Then when retuning of the controller is required, then we need to set the setting value, reference input value to 0, R to 0, and disconnect the controller and put a relay in the feed forward path. That is how upline identification is done using relay control systems. Now, for identifying specific transfer function models for process dynamics, let us assume a first order plus date time process model of the form G s is equal to k e to the power minus d s upon T s plus minus 1. So, when plus sign is used in the denominator, at that time we shall get a stable process model, whereas for the negative sign we get unstable process model. Now, in the process model we have got 3 unknown parameters. The unknown parameters are k, d and t. K is the steady state gain of the process, and k is also equal to G 0. That means, when we take the limiting value of S to 0, G s gives us the steady state gain of a process. Then D is the time delay of the process model, whereas T is the time constant of the process transfer function model. Let the controller be a PID controller given by GCS is equal to Kc times 1 plus 1 upon TIS plus TDS upon beta TDS plus 1, where Kc, Ti, Td are the parameters of the PID controllers, and beta is the filter constant, derivative filter constant. So, we will not concentrate on the dynamics of PID controller, because we are going for upline identification, where controller will be out of the loop. So, it has no role to play. Now, to identify the dynamics of an unknown process, let the process be assumed as the unknown. We do not know the dynamics of this process, rather the dynamics of this unknown process will be modeled by a first order plus date time transfer function model. Now, for that, during upline relay test, GC is replaced with a relay, then we get limit cycle output from the closed loop. So, the relay induces limit cycle output as shown here, where the output signal YT output signal has got some parameters. Since we are getting sustained oscillatory output, therefore, we can acquire or measure some information from the limit cycle output. So, let A be the peak amplitude of the limit cycle output signal. So, the A is the peak amplitude of the limit cycle output. Then similarly, P u be the ultimate period of the limit cycle output. Ultimate period means nothing but the time period of the output signal. Then the upper waveform gives us a typical limit cycle output waveform for the relay control systems, whereas the bottom one, the waveform shown below the upper one, is nothing but a typical relay output waveform. This is the relay output waveform of the same period of the output limit cycle output. H is the peak amplitude of the relay output waveform, where H is also nothing but the amplitude of relay, often known as relay height, and is the nothing but a parameter for relay setting. H is we get from the relay setting. So, when the autonomous relay control system is considered, we get some typical limit cycle output of the unknown process of this form and some typical relay output of this form. So, making measurement of some features of the limit cycle output, the features known as A, P, U of the limit cycle output, it is possible to establish some relationship with the unknown transfer function model parameters with the measurements, and then using the measurements it is possible to estimate the unknown parameters of a transfer function model, first order plus date time transfer function model. So, the relay is substituted by its describing function for the analysis. The relay is defined by a function n a, which is equal to 4 h by pi a, where h is, as we know, the relay amplitude and a is the peak amplitude of the relay input, I can say relay input signal. So, from an ideal, for an ideal relay, the describing function of the relay can be given as n a is equal to 4 h by pi a. Next, the critical frequency is defined as omega c r is equal to 2 pi upon p u, where p u is the ultimate period of the limit cycle output, ultimate period of the limit cycle output. Then, since the characteristic equation of the relay control system, closed loop control system is 1 plus n a g j omega c r is equal to 0. This is the characteristic equation of the relay control system. Then, using that we can write n g j omega c r is equal to minus 1. The same expression can be obtained from the fact that limit cycle output is obtained when the loop gain is equal to 1 and loop fetch is equal to minus pi. So, the same can be transformed into some analytical expression form, which is given as n g j omega c r is equal to minus 1. Now, substitution of n a, which is nothing but 4 h upon pi a, and g j omega c r gives us the equation 4 h upon pi a k times e to the power minus j omega c r d upon j omega c r t plus minus 1 is equal to minus 1, because n a is equal to 4 h by pi a as we have seen earlier, and g S is equal to k e to the power minus ds upon T s plus minus 1. So, in frequency domain, that can be written as j omega c r is equal to k e to the power minus j omega c r d upon j omega c r t plus minus 1. So, substitution of this N A and g omega c r over here gives us this equation. Equating the magnitude of both sides of the equation, we get 4 h upon pi a times k upon omega c r t square plus 1 root is equal to 1. So, for both the stable and unstable transfer function model, the magnitude of the analytical expression will be same. So, this can further be simplified and written in the form of omega c r t square plus 1 root is equal to 4 h k upon pi a, implies omega c r t square plus 1 is equal to 4 h k upon pi a square. Then next, that can be also written as omega c r t square is equal to 4 h k upon pi a square minus 1. Then taking the square root of that will give us omega c r t is equal to 4 h k upon pi a square minus 1 root. So, finally, we get the expression t is equal to 4 h k upon pi a square minus 1 root upon omega c r. So, this is how we get the expression for the time constant of the transfer function model, the first order transfer function model, expressed as t is equal to 4 h k upon pi a square minus 1 root upon omega c r. This expression can be used for both stable and unstable process dynamics. Next, equating the phase angles of both sides. Again we know that the phase angle of both sides means 4 k h upon pi a e to the power minus j omega c r d upon j omega c r t plus 1. Let us consider the stable process model first. So, this angle should be equal to minus pi, because the loop phase is equal to minus pi, which can be written in the form of minus omega c r d minus tan inverse omega c r t is equal to minus pi. So, making all these minus to plus now will enable us to write omega c r d is equal to pi minus tan inverse omega c r t, which will ultimately give us d is equal to pi minus tan inverse omega c r t upon omega c r. So, this is how we get the expression for the second unknown parameter in the transfer function model of a stable process dynamics. The d, time delay h, d is equal to pi minus tan inverse omega c r t upon omega c r. So, extending the similar analysis for the unstable process now, we can get the expression for d h. D is equal to pi plus tan inverse omega c r t upon omega c r. So, this is the way we can estimate the unknown model parameters t and d of the first order plus date time transfer function model using the measurements of p, u and a. Please keep in mind d and t. If we see, t is now a function of a and omega c r. and omega CR is a function of PU. Therefore, making use of the measurements of measurements of PU ultimate period and peak amplitude A, it is possible to estimate T and it is possible to estimate the Ds for stable and unstable processes. So, from the analysis we have found that with the measurements of peak amplitude and frequency of the limit cycle output signal, it is possible to estimate two parameters of the unknown transfer function model, first order plus date time model of a process dynamics. Let us go for some simulation study and see how accurate is our method. So, in the simulation study 1, let us consider the process to be process dynamics, actual process dynamics to be G s is equal to e to the power minus 2 s upon 10 s plus 1. So, the actual process is assumed to have a time delay of 2 seconds, a time constant of 10 seconds and a steady state gain of 1. So, this is the actual process has. Assuming that the actual process dynamics is not known, we shall put a relay in the feed forward path along with the process and make one relay control system. So, using the relay control system and with the setting of relay amplitude of h equal to 1, relay amplitude h equal to 1. What do we get? We get a typical limit cycle output of this form, where this is x axis is the time axis, time in seconds, and y axis is the output, limit cycle output. Now, we can make measurements, the period of the limit cycle output upon measurement gives us Pu to be of 7.332 seconds. Similarly, the peak amplitude is found to be of magnitude 0.181. So, this is a value 0.181 and Pu is of value 7.332 seconds. Then the critical frequency is calculated as omega CR is equal to 2 pi upon Pu is equal to 2 pi upon 7.332 is equal to 0.857 second, radian per second. Now, the steady state gain is assumed to be 1. As we know that using the describing function technique, we can estimate at most 2 unknown parameters of a process model. Therefore, we have to make use of some assumption, because the first order plus date time process transfer function model has got 3 unknowns: the steady state gain, the time constant and the time delay. So, the steady state gain is assumed to be known a priori, or it can be obtained from some other tests. So, assuming the steady state gain to be 1, k is equal to 1, the t can be, the time constant can be estimated as t is equal to 4 h k upon pi a square minus 1 root upon omega CR is equal to 4 into 1 into 1 upon pi into 0.181 minus square minus 1 root upon 0.857 gives us t is equal to 8.1249 seconds. Similarly, d is calculated using the measurements h. D is equal to pi minus tan inverse omega CRT upon omega CR is equal to pi minus tan inverse 0.857 into 8.1249 upon 0.857 is equal to 1.9993 seconds. Thus, the process model parameters time constant is found to be of value 8.1249 seconds instead of the actual value of 10 seconds, and the time delay is of value 1.9993 seconds instead of or in place of 2 seconds. Those are the actual plant parameters, or the actual process has got the dynamics with time constant of 10 seconds and time delay of 2 seconds. So, the model parameter time constant is underestimated by 18.75% and the time delay is underestimated by 0.035%. So, we can tell that the time delay has been estimated accurately, whereas the time constant has not been estimated accurately. Since the relay has been assumed by its equivalent gain, therefore, there is estimation error in the identification scheme. If the relay is approximated by its exact gain, or if the relay is substituted by its exact gain, or making use of the exact analysis of relay control system, it is possible to estimate the model transfer function model parameters accurately, whereas we have to sacrifice some accuracy in the case of a relay control system using some describing function technique. Let us go to one more simulation study, where the unknown plant dynamics is assumed to be G s is equal to 1 upon s plus 1 to the power 5. So, in this case, what we are going to do, the actual plant is a plant all pole plant with 5 repeated poles located at s equal to -1. So, the actual plant is something else, whereas we are going to estimate the plant dynamics by some first order transfer function model. What is that model? So, we are going to estimate this dynamics by some equivalent model GMS of the form k e to the power minus ds upon Ts plus 1. So, it is possible to capture the dynamics of actual plants by some transfer function models. Not necessarily one has to assume the form of the transfer function as same as the plant dynamics. In that case, a symmetrical relay with amplitude h equal to 1 produces a sustained symmetrical process output, and making measurement of the limit cycle output signal, we obtain the peak amplitude to be of A is equal to 0.474 and the peak and the ultimate period is of value 8.732 seconds. So, the critical frequency is calculated at omega CR is equal to 0.7196 seconds. Again, assuming the steady state gain to be 1, T is calculated H, T is equal to 4 h k upon pi a square minus 1 root upon omega CR is equal to 3.4645 seconds. So, the time constant of the transfer function model is computed or estimated as t is equal to 3.4645 seconds. Now, the time delay can be estimated using the formula d is equal to pi minus tan inverse omega CR t upon omega CR, which is equal to 2.713 seconds. So, the time delay of the first order plus dead time transfer function model is found to be of the value 2.713 seconds. Then the unknown plant dynamics is now represented by a transfer function model given as GMS is equal to e to the power minus 2.713 s upon 3.4645 s plus 1, whereas the actual plant dynamics is Gs is equal to 1 upon s plus 1 to the power 5. So, actual plant with the dynamics given as this has been represented by a first order plus dead time model with time delay of 2.713 seconds and time constant of 3.4645 seconds. Now, how to validate the accuracy of identification? For that, what we have done? So, to ascertain the modeling accuracy, to investigate the modeling accuracy using the frequency response plots of both the actual and identified plant, we have obtained the Nyquist plots of the nominal and identified plants. So, the Nyquist plots of the original plant and the identified plants are plotted and shown over here. So, there is no significant differences between the two plots, then one can conclude that the identified model truly represents the dynamics of the actual process. So, basically we have concern about the part of the Nyquist plots in this range of frequencies, and as we see there is no much difference between the two plots. Therefore, we can tell that we can assume that the identified transfer function model represents the dynamics of the actual model, actual plant successfully. Now, for the transfer function model having some generality and given as Gs is equal to k e minus T0 s plus 1 times e to the power minus theta s upon T1 s plus 1 to the power p. Also, we can make use of the describing function analysis and estimate the unknown parameters of the transfer function model. Now, here the transfer function model involves a lot of parameters, the steady state gain k, time delay theta, here theta is the time delay of the transfer function model, T0 is the time constant of the transfer function model, and T1 is also one time constant of the transfer function model, and P is the pole multiplicity a transfer function model H. Then for various values of P, we get different type of transfer function models, and similarly for various values of theta and T0, it is possible to get transfer function model with time delay and transfer function model with non-minimum phase characteristics. Now, when lambda is assumed as lambda is equal to minus 1 upon T1, when P is equal to 1, for the case T0 is greater than 0 and theta equal to 0. Theta equal to 0 means we basically get the non-minimum transfer function, non-minimum phase transfer function models. So, for those models one can establish equations or relations using describing function for the relay control system, and the set of equations can be obtained as the peak amplitude can be given as A is equal to 4 kh upon pi root of 1 plus omega CR T0 square upon 1 plus omega CR upon lambda square. Similarly, this we get from the loop gain condition, and similarly the loop phase condition enables us to obtain an expression of the form pi minus tan inverse omega CR T0 plus tan inverse omega CR upon lambda is equal to 0. So, basically we are able to obtain two relations, two equations using the describing function analysis. Similarly, when T0 is equal to 0 and theta is non-zero, that means when the transfer function model is a transfer function model with time delay. For that case, A is given as 4 k h upon pi cos pi minus omega c r theta, and the phase condition of the relay control system will give pi minus omega c r theta plus tan inverse omega c r upon pi is equal to 0. So, in any case, what we have found, we are able to get two equations using the describing function analysis. So, for higher values of p also, one can easily obtain similar expressions when p is equal to 2. When the transfer function model is of second order, in that case, for the case of t 0 is greater than 0 and theta is equal to 0, the set of equations are obtained as A is this much and the phase condition gives us this equation. Now, for t is equal to 0 and theta is not 0, for transfer function models which are known as time delay models. So, time delay models, then the two equations are A is equal to 4 k h upon pi cos square pi minus omega c r theta upon 2, and the phase condition will give us pi minus omega c r theta plus 2 tan inverse omega c r upon lambda is equal to 0. So, these equations can easily be obtained using describing function analysis, and it is not difficult to obtain similar expressions for higher values of p. So, for p from 3 to onwards, 3, 4, 5 onwards also, we will get very simple analytical expression of these forms. Now, drawbacks of an upline relay test. What are the drawbacks an upline relay test has? Using the describing function, the upline relay test is found to give us only two analytical expressions. Therefore, two unknowns of the transfer function model can be estimated. So, basically we make use of the measurements and the analysis to estimate the time constant and time delay of a transfer function model. In that case, it is required to estimate the steady state gain by a separate relay test or using some other analysis, because we cannot estimate three unknowns using the two equations we developed for the relay control system. So, one has to either assume the steady state gain to be known a priori or make use of other tests to estimate or obtain the steady state gain value. So, that is one of the major drawback associated with an upline relay test. Now, second problem with the upline relay test is that it is sensitive to the presence of static load disturbances. How that is so, we shall see by going back to some earlier slide where we have the structure for relay control system. Now, this structure shows that when the relay is connected with the process, unknown process, when some static load disturbance is present, in that case what will happen? The process input will be asymmetrical. As we know, when L is equal to 0, what will be the form of the U? U will assume some symmetrical output waveform of the form some square or rectangular pulses. So, this is what we have T and this is our U T. This is what we get when L is equal to 0, when the static load disturbance is equal to 0. Suppose L is of some magnitude and the relay amplitude is 1, therefore, magnitude of this signal is equal to 1. Now, when L is equal to 0.5, then this 0.5 will get superimposed with this signal and ultimately it will get elevated. Therefore, we will have some asymmetrical relay output signal of the form shown over here. So, this will continue, this is the time and this is the ut. So, for this case, for this situation, what will happen? When the input signal to the process is asymmetrical, the output, the limit cycle output also will be asymmetrical. Definitely it will be asymmetrical, but of the same period as well. So, we shall get some asymmetrical limit cycle output, asymmetrical limit cycle output from the system. So, although the relay is symmetrical, whereas the limit cycle output signal is asymmetrical. Now, how to make use of those techniques, the analysis we have made earlier, all those will fail because we cannot get correct measurement of the peak amplitude. Now, we have got two peaks, one positive peak and one negative peak of different magnitudes. Similarly, the period we can measure, but when we resort to half period, there will be lot of difficulties. So, again measurement of period will be there, but we will not get the correct period what is required for the symmetrical relay. So, when the asymmetrical output limit cycle output is obtained, we do not know where from the asymmetricity is coming. So, is it due to asymmetrical relay or is it due to disturbances? That will actually create problem. We may not get correct information about the process dynamics. So, that is one major difficulties associated with offline relay test. So, the offline relay test is subjected to limitations and inaccuracies when the static load disturbances are present, and in practical real time systems it is very difficult to avoid static load disturbances or some form of disturbances will always be there. Therefore, the offline relay test may give us inaccurate estimation of transfer function model parameters. Now, third point is often it is dangerous and also expensive to break the control loop for the purpose of tuning only. For the purpose of PID controller tuning, when the loop is broken, then the control operation is disrupted, the normal operation of the system gets disrupted, which is not desirable for many real time systems. What is desirable rather, that often it is desirable to tune controller under tight continuous closed loop operation. So, desirable is to tune controller under tight closed loop operations, and this is what we are not going to get from offline tuning schemes. Next, we shall consider some online identification structure to overcome the limitations associated with offline identification schemes. We shall consider an online identification structure, where this RT is not necessarily has to be 0. So, I can write it can be non-zero also. This is your RT or reference input R simply. So, this gives us the structure of an online identification scheme. What we see, what is the basic difference between the earlier structure and this structure? A relay has been connected in parallel with the controller. A relay has been connected in parallel with the controller, and the controller remains in actions throughout the operation of the real time system, real time process. Whereas, whenever there is requirement for retuning the parameters of the controller, what we can do? The process information can be acquired by setting some relay amplitude. So, when the relay amplitudes H is equal to 0, when the relay amplitudes H are 0, at that time the controller is in action and the output of the plant can be of the form like this. We do not get limit cycle output when relay is not in action. Whereas, when the relay is in action now, when the relay amplitudes are not equal to 0, at that time we will get the output of the form limit cycle output superimposed over the steady state output of the process. This is the beauty. So, during this time we make measurements of the output limit cycle output signal and estimate the plant dynamics model parameters. So, plant model parameters, and based on the model parameters, the parameters of a controller are set. The parameters of a controller are set, and this is how online identification and tuning is done in real time. Now, we can represent the online identification structure by some equivalent diagram. If you look carefully, then in that case again R is not equal to 0. Then the GS is now subjected to some inner feedback with a controller GCS. The earlier feed forward path controller GCS now appears in the feedback path. So, GS is now having some inner loop controller GCS, and relay basically sees or experiences the process connected with an inner controller. So, the relay is experienced or experiences or sees a, I can say, a controlled process, a process with a controller in the loop. Now, in contrast to the upline control scheme or the conventional relay control scheme, the relay is subjected to a closed loop system. Earlier, the relay was subjected to the process dynamics only, whereas in the online identification scheme, the relay is subjected to a process with a controller in the loop. Therefore, it is possible to estimate more than 2 parameters from this scheme also. With proper use of the or with proper measurements of the limit cycle output signal, it is possible to make more measurements from the limit cycle output or the output of the relay control system, and it is possible to estimate more than 2 unknown parameters of a transfer function model. So, basically an online identification scheme has got advantages over the upline identification scheme in the sense that the planned operation is not disrupted. So, we will have normal operation of the plant, and the relay heights are to be or the relay amplitudes are to be chosen suitably such that the plant operation is not affected at all. So, one can put some conditions depending on the magnitude of the error signal E the error signal. So, whenever the error signal is greater than some threshold value epsilon, that time only relay will come into picture will be in action and induce limit cycle output, and when the error signal is less than some threshold value, there is no need for retuning the PID controller parameters. So, this is the beauty of online identification scheme. Now, using the online identification scheme, a suitable controllers also can be designed. The form of the controllers also can be decided upon. So, those issues will be discussed in the next lecture. Next, we shall go to the summary now. What we have seen in this lecture? Upline process identification is presented. So, an upline identification scheme is presented, and it is found that it is possible to estimate two unknown parameters of a transfer function model using the describing function gain or using the describing function analysis of a relay. Now, first order plus date time transfer function models can be estimated or obtained using the measurements made on the limit cycle output. Not only first order plus date time models, but also we can estimate, we can obtain transfer function models of various forms, and those are nothing but non-minimum phase transfer function models and higher order time delayed transfer function models. In that case, what we will have? Second order plus date time transfer function model, third order plus date time transfer function model, and so on. So, it is possible to estimate two unknown parameters of non-minimum phase transfer function models, or first order plus date time transfer function models, or second order plus date time transfer function models, or third order plus date time transfer function models using describing function. Next, now it is not possible to estimate accurate values for the steady state gains using upline relay identification scheme. So, estimation of steady state gain has to be done by some separate test or by some other techniques. So, this is one crucial issue, and there is limitation with the upline relay test, mainly in estimating the steady state gains. Now, coming to the next point, as we have discussed, often it is dangerous and expensive to break the closed loop operation for the sake of tuning of controllers, and to overcome that we have introduced online identification schemes. So, online identification schemes can be of different types. One such online identification scheme has been introduced. We can have other type of online identification scheme as well, where the scheme can be given in the form of, suppose, a relay outside the closed loop, then we will have the controller, the process, inner feedback, and then we can have the feedback, negative feedback to relay. So, this can make a probable scheme for online identification also. Here in this case, what is happening? When the relay amplitudes are 0, we have got the normal operation of the plant or process with a controller, and for non-zero heights of the relay, or when the relay amplitudes are not 0, at that time the output will have some limit cycle waveform, and this also can make a probable candidate, as I have told, for the online identification scheme. scheme. Some points to ponder: how difficult is it to identify a varieties of transfer function models? Describing function based methods enables one to estimate two unknown parameters of a transfer function model. As you have seen, the model can be of a general form or of any form, but only two unknowns of the transfer function model can be estimated using the describing function analysis. So, some other tests or multiple relay tests might be used, might be made to identify a varieties of transfer function models. The second point: how is the identification scheme sensitive to external disturbances? As you have seen, when we have got a static load disturbance, then the limit cycle output becomes asymmetrical in spite of using a symmetrical relay in the relay control system, and asymmetrical relay output may not give correct information of the process dynamics. To avoid that, what has to be done? As far as possible, we should try to get symmetrical limit cycle output, and we should try to take measurements from the symmetrical limit cycle output. And for that, one has to make use of some other scheme, and one has to go for online identification scheme. Also, it is possible to make use of another analysis technique known as dual input describing function analysis, DIDF analysis for the relay control system, which is subjected to external static load disturbances. So, in this case, it will be possible to estimate more number of parameters, and also it might be possible to estimate accurate values for the transfer function model parameters. That is all in this lecture. Thank you.